Hey folks, last time we talked a little bit about science in general. Today I want to give you a quick intro to physics, a little bit more specifically about what we're going to be looking at this year. This won't be quite as long as our last video. So, book definition of physics, the branch of science concerned with matter and energy, especially as they relate to mechanics, which is motion and forces, heat or thermodynamics, electricity, and that's both current and static electricity, magnetism, which is awesome, including electromagnetism, and then atomic phenomena. So these are the big things that we're going to be talking about this year. We're going to talk about motion. We're going to talk about motion in a straight line. We're going to talk about circular motion. We're going to talk about rotational motion. And then we're going to talk about the forces, both balanced and unbalanced, that cause all of these different types of motion. We're going to talk about heat, the transfer of energy from hot things to cold things. We're going to talk about specific heat and some other ideas that hopefully you will recall from chemistry. We're going to talk about electricity. We're going to talk about static electricity and how powerful it can be. We're going to talk about current and circuits. We're going to build circuits. We're going to build circuits that create magnetism, electromagnetism specifically. We're going to talk about how permanent magnets work and why they work, and the Earth as a large magnet, and how important that magnetic field is to our survival on a daily basis. And then we're going to talk about the structure of the atom and how atoms interact with each other. And a lot of that, again, hopefully is some chemistry review. But what's really cool about physics is that physics is kind of the foundation upon which all of our other sciences are built. And so as we go through the year, you're going to see some things that might remind you of stuff that you've talked about in chemistry or in biology or in earth science. Because physics really is a foundational, well, we'll talk about that in a minute. But when we learn physics, we're not just learning about how the world works. Hopefully, as we go through the year, you're going to be developing some critical thinking skills that allow you to look at the world around you and better understand what's going on, the ability to question what's going on around you better, not just from a scientific perspective, but from all perspectives. And once we understand physics, everything else becomes so much easier to understand. You can look at the carbon cycle in plants and everything starts to make a little more sense. You can look at chemical reactions and the why, the what's going on in between those atoms starts to make a little more sense. Physics really is the most basic of our sciences. Chemistry then takes that and explores how everything gets put together. And then biology takes that chemistry piece and looks at how it applies to living things. Here's a nice little pyramid, I think, that kind of explains this idea. We have physics at the bottom. Chemistry is built on the foundational principles of physics, and biology is built on the foundational principles of chemistry. I love the comic XKCD. That's what this is from. If you're not familiar with XKCD, if you have any type of science or tech or just nerdy inclinations, they're comics that come out 3 times a week, and they're fantastic. They cover all different types of things, from computer science, physics, biology, technology. It's just really cool. And so this particular one, it says fields arranged by purity. The least pure are on the left, and we get more and more pure as we go from left to right. And so over here on the left, you have your sociologists looking forlorn and sad because they are farthest to the left. And then you have your psychologists saying, oh, well, sociology is just applied psychology. And we work our way to our biologists with our delightful little octopus. And then our chemists saying biology is just applied chemistry. And then you have your happy-go-lucky physicist over here, feeling quite smug and proud of himself, saying, which is just applied physics, it's nice to be on top. If you've seen this before, you might realize that this isn't the entire comic. If we zoom out just a touch, and this is for Mr. Snyder in the math department, although this is not Mr. Snyder, this is maybe Miss Jason, because it is clearly a girl. Here's our mathematicians here on the right saying, oh, hey, I didn't see you guys all the way over here. The point here being that physics really is just applied math. What physicists attempt to do is find those mathematical relationships between variables in the universe and use that to explain or to create laws about how the world works. And as part of that, mathematics really is not just the language of physics, although really it's fundamental to physics. It's a language of science in general. Scientific findings. Anytime you read a scientific paper, you have data tables, you have graphs, you have equations that have been developed in order to express whatever it is that that particular scientist is trying to explain. When you can boil things down to mathematical expressions, they're so much easier to verify or disprove by experimentation. Now, notice we didn't say prove or disprove, right? This term, prove, is not one that we are going to use this year. And the distinction between verifying and proving, right? When we verify something, we find evidence that supports an idea, a law, a theory. In order to truly prove something, that something is a fundamental aspect of the universe, we would have to test it in every imaginable, every possible situation and find that it occurs, that it is true in every single situation. Now, clearly we have laws, and clearly those laws have not been tested in every single possible situation. So there has to be a little bit of balance. We have our laws, our fundamental laws of physics, of biology, of chemistry. But scientists understand that those are only laws until evidence comes along that disproves it. And as we kind of look at these two terms, prove and disprove, you only need a single instance of a law to not hold true in order to disprove it. You would need an infinite number of pieces of evidence that a law is true in order to prove it. And so it's much easier to disprove theories, much easier to disprove laws. And so that's it. That's even like at the scientists in a lab level. As we work through here, as we're learning about the world around us, there will never be a time where we are going to prove something is true. And so we're not going to use this term in our vocabulary. It is not going to be in our vocabulary this year. We will support, absolutely, we will find evidence that supports ideas. We will find evidence that helps to verify. We will find evidence that does not disprove. But we will not prove anything as we work through this year. So something to keep in mind. The other nice thing about our mathematical language is that when we express ideas in terms of mathematical relationships, they're unambiguous. There's not room for interpretation. It is or it isn't. Here is our mathematical relationship between distance and time. It is or it isn't, right? If suddenly that changes, then now we've disproved what we just found. It simplifies things, right? It gets rid of a lot of the verbiage. If we can compress a bunch of lofty ideas down into a couple simple, straightforward mathematical equations, which we'll refer to also as models, mathematical models, as the year goes on, then it helps us to see how different variables relate to each other. So something to keep in mind. And we're going to be doing a lot of math this year. We're going to be doing a lot of algebra. Hopefully those of you who take calculus will recognize the calculus connections. Calculus was essentially created, was invented for physics because the math of the day couldn't handle the calculations and the expressions that the scientists wanted to show, and so a new form of math was created that would allow them to do so. And that's where we get into integrals and derivations and things like that. I'll try and show you some of that as the year goes on, but it's not going to be an expectation. As long as you are comfortable with algebra, you will be fine this year. We will get into some trig. You'll have to handle sine, cosine, tangent throughout the year and work with triangles and things like that, but nothing more complex. So, long and short, math is awesome. Math applied to physics is even more awesome. Physics in general is the most awesome.